What's up, scholars? Today we're talking about the fundamental theorem of algebra. Algebra, I thought this was pre-calculus. It is pre-calculus, but it's based in algebra. Also, fun fact, since we're talking about fundamentals, fun fact, you are best at the math topics you studied 3 years ago. So if you're in pre-calculus this year, you were in either Algebra 2 or Geometry the year before, which meant you were in either Algebra or Geometry the year before. And then 3 years ago, you were in algebra. Whoa. So you're finally starting to get the hang of algebra now that you're in pre-calc. Yeah. So we're going to talk about this fundamental theorem of algebra, which states the degree of a polynomial indicates the number of roots of that polynomial. So let's do a super simple example that you've seen 1,000 times. Let's say we have f of x equals x squared minus 9. What's the degree of this polynomial? It is the highest exponent, so the degree is 2. The degree is 2, which means we should have 2 roots. Now if we put this in factored form, this would factor to x minus 3 and x plus 3. Yes. And when we graph this sucker, we would see 1, 2, 3, 1, 2, 3. We would have a root at positive 3 from this guy, right? Because you said each of these equal to 0 and solve. And we would have, there's my cat coming to join us, a root at negative 3 from this guy. And it's a positive even function, so it goes up on both sides. It would look something like this. We have 2 roots because this is degree 2 quadratic. Easy peasy lemon squeezy. Okay, so let's say we had this guy, x squared minus 8x plus 16. If we put this in factored form, we'd get x minus 4 times x minus 4, which would mean we would plot this, and maybe we set both of these equal to 0 and solve. We'd get x equals 4 in both places, 1, 2, 3, 4. So we would only have one distinct root, because both of these, when solved, x minus 0 equals, or x minus 4 equals 0. So if both these equal to 0 and solve, you would get the same answer both times, which would be positive 4. This is a positive even function, goes up. This only has one root, you liar. It's supposed to have 2 roots. What's going on? Well, it has one root with a multiplicity of 2, because the one root comes from 2 different places. So this has one root multiplicity of 2. So that's where we get our 2 roots for our quadratic here. Okay, so let's say we have f of x equaled x cubed. You know what? We can do this right away, because this is one of our parent functions. This is a cubic function. We know what this one looks like without doing any of that factoring stuff. And we know from what we just talked about, we're going to have 3 roots, because the degree of this polynomial is 3, right? We're going to have 3 roots. So we graph this based on what we remember. It's a positive odd function. It goes right through here like this. What? We only have one root. We only have one root? We're supposed to have 3 roots. This is a cubic function. Well, if we did factor this, this would come from x minus 0 times x minus 0 times x minus 0, which means all of these roots, we would get an answer of 0. So this one root has a multiplicity. It shows up 3 times. multiplicity of 3. So that's where our 3 roots come from to match up with our degree 3 polynomial. Let's do a little multiplicity summary here. We're going to draw one big graph. Okay, we're going to start down here. We're going to go through the x-axis. Then we're going to come and just touch it and go up. Then we're going to come and hang out for a little bit and go down. And I'm going to go straight through one more time. Okay, so you can tell the multiplicity of each 0 by how it crosses the x-axis. If it goes straight through, it has a multiplicity of 1. So this graph goes straight through the axis. It has a multiplicity of 1. Where else does that happen in this picture? Right here. This goes straight through, has a multiplicity of 1. Okay? If the graph goes down to the axis, touches it, and goes back up in the same direction. Boom, boom. So it like bounces off. That is a multiplicity of 2, which we saw in our quadratic function, right? We have this quadratic function, came down, bounced, went back up, has a multiplicity of 2. And finally, if it comes, hangs out, and then continues going in that same direction. So this was down and down. This will be a multiplicity of 3, like we had in our parent cubic function. So again, the multiplicity in this graph is indicated by the circled number. The circled number. If it goes straight through a graph, multiplicity of that 0 is 1. Straight through a graph, multiplicity of that 0 is 1. If it comes to the axis, touches, and bounces off like boom, like a ball maybe, bounce, that is a multiplicity of 2. And then if it hangs out for a minute and keeps going that same direction, that's a multiplicity of 3. So based on this graph, what would be the degree of this strange polynomial? Well, we would add up all the multiplicities. So degree of this poly would be 1 plus 2 plus 3 plus 1. 1 plus 2 plus 3 plus 1. What is that? 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 1 is 7. This would be a 7th degree polynomial. So something along the lines of f of x equals something to the 7th plus blah 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 blah. Probably a lot of garbage at the end. Up to adding some constant, which we would be at the 8th letter of the alphabet, which I'm not sure what that is. So I'm just going to pretend it's the letter Z, which it's clearly not. The degree of this polynomial is the sum of its multiplicities. Alright, you can have higher multiplicities than 3. Like, for example, if we had f of x equaled x to the 4th, if you graph that, you will find that looks shockingly like our quadratic function, and it will only go through the x-axis one time, but we're supposed to have 4 roots here, so we know implicitly that we have a multiplicity of 4. But this is the most common. 1 when it goes straight through, 2 when it bounces off, and 3 when it kind of changes its direction there. Alright, let's say we have f of x equals x squared plus 9. Alright, I got it. This is a degree 2 polynomial. It's going to have 2 roots. Well, if we graph this, it's going to look like this, which would apparently have no roots. What? Well, first of all, this isn't factorable. But if we set this equal to 0 and try to solve, we subtracted 9 on both sides, and we got x squared equals -9, and we're just following this along. We square root both sides, we get x equals plus and minus. The square root of -9 is 3i. We've got imaginary roots because we are square rooting a negative number. We square rooted both sides. We square rooted a negative number and got an imaginary number. So we do have two roots. One is positive 3i, one is negative 3i. We just now have two complex roots. Holy cow. Alright, so we can have, recap here, we can have simple, normal, easy functions that go through the x-axis the exact number of times per the degree. Great. We can have not quite as simple, where we have one root and multiplicities that get us to the degree of that polynomial. We can continue that on with having one root with higher multiplicity of 3. Here's our multiplicity chart telling us what these multiplicities look like. But we know that can go even higher than our little chart here. These are just the most common, so we plotted those out. And now we see that we can have complex roots. All this to say, the degree of the polynomial indicates the number of roots of the polynomial. They just could be complex, and they could have various multiplicities. Alright, let's go check out some delta math, shall we? I think we shall. Alright, first question. Finding roots from a graph. The graph of y equals f of x is shown below. What are the real roots of this equation of f of x equals 0? So, we're really just finding the numbers where this graph crosses the x-axis. So it looks like it's at -5. We've got a root at -5. We've got a root at 2. And we've got a root at 8. Great. And all of these cross straight through, so they have a multiplicity of 1. So this must be a cubic function. Are we sure? Yes, I'm sure. Awesome. That's not bad. Alright, how about this one? Select an equation from the roots, level 1. Which equation choice would represent the graph below? Ah, okay, so these are in factored form. Gotcha, and they're gonna relate to the zeros here. So remember, when we're in factored form, we set each of our factors equal to 0, so to solve for the zeros. So this 0 here at +7 must have come from a factor that was x minus 7, right? Because we would have set that equal to 0 and solved and gotten +7. So this root at +7 must have come from x minus 7. This is at 0, so this would have just been x equals 0. Maybe I'll just write all this out. X equals 0. We set all these equal to 0. Thinking way back in there. And this -6 must have come from the factor that was x plus 6 equaling 0, because we'd solve that and get a -6. So here are the factors we're looking for: x plus 6, x by itself at x minus 7, which means we are looking for -7 and +6, right? It should be that very first one. Let's click it. -7 plus 6, submit our answer. Yeah, dude, I'm ready to go. Give it to me. That's right. Genius. Okay, select equation from graph roots level 2. Which equation choice would represent the graph shown below? We have one root here, but this is a cubic looking thing, so we should have 3 roots, which means we have 2 complex roots. And we had complex roots that showed up when in our equation we had, remember we had a squared plus, so think back to your notes, we had something that was like x squared plus 9, and that got us to x equaled plus or minus 3i. That gave us the complex roots. So we're going to want to look for something that's x squared plus a number. X squared plus a number will get us these complex roots. Okay, gotcha. It's probably not going to be plus 9 since all of these are, none of these have the number 9 in here. I'm just reminding us of what we talked about before, how that's related to complex roots. I do see this one, this normal root at negative 8. That must have come from the factor x plus 8. X plus 8, right? Because that would have equaled 0. Let's set that equal to 0 and get the number 8. So we're looking at either this top choice, because that has the x plus 8, or this bottom choice here. Well, that's not bad, because we just talked about that we need x squared plus a number to get some complex roots, x squared plus a number, so that must be our very first choice. Very first choice, turn off my thing there, submit it, because that x plus 8 comes from here, the x squared plus a number is what gives us our complex root. Submit our answer. Are you sure? Yeah, dude, I'm sure. Give it to me. Select equation from graph roots level 3. Which equation choice would represent the graph below? Good thing we're a bunch of geniuses over here. Bunch of geniuses. Let's see what we got. We've got a root here at 3. It's going straight through. There's a multiplicity of 1, so that must have come from the factor x minus 3, right, equaling 0. Cool, I see that, x minus 3. We've got another root here at 1, but this goes up and bounces off. So that must mean we have a multiplicity of 2 at this root. So that must mean we have x minus 1 twice. X minus 1 and x minus 1. We've got a multiplicity of 2 at this root at 1, so it must have showed up twice, which would be the same thing as x minus 1, oops, sorry, I got bad, x minus 1 squared. X minus 1 squared. Hopefully you're listening to my words, not just copying down the pictures. X minus 1 squared. So we're looking for x minus 1 squared and x minus 3. X minus 1 squared and x minus 3. There she blows. Select, submit. Yes. Yeah. Alright, scholars, that's it. That's the fundamental theorem of algebra. Nicely done. Way to go. I love you so much. I will see you next time. Keep on that hustle.